Okay, so we finished this chapter by looking at the last three important lemmas that will be used as building blocks of the main results of this course. Oh la la. Uh, okay, the first one is the joint typicality lemma, which can be stated as follows. Oh my goodness. It's getting cold, you see. I have to put on a sweater. So joint typicality lemma says the following. Basically, it's a bound on the probability that two independently generated sequences that are individually typical happen to be also jointly typical. But we want to formulate this in a sufficiently general form that will be useful in several different proofs as a building block. So we consider a conditional version of this lemma that says the following. So suppose that we have three, in fact, PMF, the joint PMF of three random variables that I call u, x, and v. So P sub u, x, and v, which defines a typical set, a jointly typical set, and fix arbitrary sequences u and x, and then generate another random vector that I call y tilde according to a product distribution of y given u. So what is y given u? Y given u is the conditional marginal distribution of y given u obtained by marginalizing the joint px, ux, and y. So in other words, from the joint distribution we can derive all other marginals and conditionals. So this is the conditional y given u induced by the joint PMF P, U, X, and Y. So we generate this new random vector according to this product distribution for a given sequence U, and we look at the probability that this randomly generated sequence y tilde is jointly typical with the U and X picked before, fixed sequences. And this probability is upper bounded by 2 to the minus n times the conditional entropy of x and y given u minus a small quantity, where as usual by delta of epsilon I indicate quantities that are vanishing, they go to 0 when epsilon goes to 0. Then we have a statement number 2 that says now instead of picking x and u fixed, we pick a random u tilde and x tilde distributed according to some joint distribution that I don't care. This q has nothing to do with p. And then again, we generate y tilde in the same way as before. Now it's conditioned with respect to u tilde sequence. And the probability that the random u tilde, x tilde, and y tilde are jointly typical with respect to the typical set induced by p u x y is again upper bounded by the same exponential as before. And finally, the last sentence says that if I now pick epsilon and epsilon prime in this order, epsilon greater than epsilon prime greater than 0, and sufficiently large n, if u and x are jointly epsilon prime typical, and I generate y tilde according to this product distribution condition on u, then the probability that u, x, and y tilde are jointly typical is upper bounded by a term that is very similar to the, lower bounded, what I'm saying is lower bounded by a term that is very similar to the upper bound. The only difference is that now this small quantity delta is with a plus, and we have this 1 minus epsilon in front, okay? But the dominating terms of all these upper bound and lower bound are always 2 to the minus n times the mutual information of x and y given u. So how do we prove this? Well, we see immediately that once we prove 1, we immediately have also 2. Why? Because this holds for arbitrary u and x, and then even when we select u and x according to some distribution, and then we take we sum over all the possible with the probability, if this bound holds for every single u and x, then it holds also on average when we average with respect to another distribution. So 1 implies 2, and then for 3 it is a bit different. We have to work it out. So statement number 1, we pick u and x arbitrary, we generate y tilde according to this product distribution. So what is this probability? Remember, every time we have a probability of an event, the event is that this triple is inside this set. This is equivalent to summing the probability of these elements over the set. So it's sum over all the y's. The only random thing here is y, y tilde. So we sum over all the sequences y in the such that x, u, x, and y are jointly typical, which means summing over, by definition, the conditional typical set of y given x and u, the corresponding probabilities. Okay. But now what we have? Well, now we have, in fact, those are typical. So those are the triple x, y, u typical, in particular y, u typical. We have this uniform upper bound on all these probabilities, which is 2 to the minus n times the conditional entropy of y given u minus some small quantity. I call it delta prime. So if I replace this uniform upper bound, then I have just the upper bound times the number of terms in the sum, which is the cardinality of this conditional typical set. Now we have an upper bound on the cardinality of the conditional typical set that holds for any conditioning individual sequences x and u, which is 2 to the n times the entropy of y given the conditioning x and u plus another small quantity that I call delta second. It doesn't need to coincide with delta prime. When I put everything together, remembering the fact that h of u, of y given x u, and this comes with a minus because I collect this minus in front of everything. So minus this plus h of y given u. Remember the following: I have a difference of entropies, of conditional entropies, where the term with the minus has an extra conditioning term, and then there is a common term. So this is a pattern that we immediately recognize as a mutual information. This will be the mutual information of x and y given the common conditioning u. Okay? So we have this, and then we have the terms, the two delta prime and delta sum up, and then give another function. But you know, if delta prime and delta second are vanishing with epsilon, also their sum is vanishing with epsilon. So this proves the statement. Now, statement 2, as I say, follows immediately, because all we have to do is simply write down this the probability of this random event. Now we have that the distribution of the triple u tilde, x tilde, y tilde is the joint distribution of u tilde and x tilde, and then the conditional y given u, which is given, right? And at this point, we have already proven that for every x and u, this term is upper bounded by this quantity. Then we sum over all possible x and u, and this sum is at most 1. So this is at most 1, and then we are done. Okay? So that's very easy. Now for statement number 3, well, so we pick epsilon and epsilon prime in this way. And then what happens? It happens that now we have that because we have that u and x are epsilon prime typical, we are exactly in the situation of the conditional typicality lemma, for which we can see that each of these probabilities, right, is in fact now lower bounded by this quantity, and now and the size of this conditional typical set of y given xu is also lower bounded by this quantity, and this is exactly the statement of this extension of the this additional property, that if we pick, in this case is x, y, and then is z. Now in the statement of the lemma, it would be u, x, and y, but you see the structure is the same. We pick the first two sequences to be epsilon prime typical. We generate a third sequence conditioned just on 1, and then what is the probability that the triple is jointly typical is 1, and this implies, in fact, implies the fact that the size of this conditional typical lemma, as we have seen here, is, where is it? Is lower by, for sufficiently large n, is lower by 1 minus epsilon times 2 to the entropy, the conditional entropy. So here is using these properties, we have that, where is it? Okay, it's here. So now we have this lower bound on the size of this conditional typical set, which is 1 minus epsilon times 2 to the n times the conditional entropy. Now the condition is xu, and then there is a minus delta second, then we put everything together again, and we get, so this follows from the conditional typicality lemma. Okay, so this proves the third statement, and now, armed with this joint typicality lemma, we can prove the final two important lemmas. But before this, let me give you an intuition behind this lemma. So now forget about the conditioning on u. Say we have only two random variables, and basically this lemma says the following: if I have a joint probability mass function for two random variables x and y that defines a jointly typical set, and then I generate x according to the marginal with respect to x, and y tilde according to the marginal with respect to y. So x and y tilde are individually distributed according to the correct marginals, but they are independent, while x and y are, generally speaking, they are statistically dependent because they have a joint distribution. The probability that two marginally typical but independent sequences are in the joint typical set, goes exponentially to 0, and the exponent is precisely the mutual information. The idea is that is precisely what I said before, that the jointly typical set is exponentially smaller than the Cartesian product of the individually typical set. Basically, we can say, okay, every x and y tilde are individually typical with very high probability, and we know that there is equipartition property. So basically, all the pairs x and y tilde are essentially equiprobable, and their probability is in fact 1 over the Cartesian product, or the size of the Cartesian product of their corresponding typical sets. Because we have equipartition property, the probability spreads uniformly over this set. What is the probability that a randomly picked pair is in fact jointly typical? Well, it's essentially this probability times the number of the number of possibilities of having a jointly typical sequence, which is n 2 to the n times the joint entropy, right? And if we take this ratio, well, this is exactly 2 to the minus n times the mutual information, because the joint entropy minus the two individual entropies makes minus the mutual information. Okay, so that's the interpretation. We pick two individually typical sequences, but they are individually typical, but they are independent. What is the probability that effectively we hit one jointly typical pair? Is exponentially small, and the exponent is the mutual information. So in particular, if the mutual information is 0, so x and y are effectively independent, this probability is essentially 1. But if the x and y are strongly dependent, their mutual information is large, we see that this probability goes to 0 very quickly when n becomes large. It goes to 0 exponentially fast according to the mutual information. So, okay, this is the intuition. And here we have the first important result that we will use in the proof of the channel coding theorem, which is called the packing lemma. So the packing lemma says the following. Suppose that I have, again, a triple uxy with its joint distribution. Then we generate u and y according to some other distribution. And then we consider a collection of sequences x indexed by n. So this set A is simply 1, 2, 3, 4 up to some quantity, and we have an exponential upper bound to the size of this set. And so we have a collection of sequences. And these sequences are generated according to the conditional distribution of Px given u, where the conditioning is exactly the u tilde, so is the same, the component of this sequence. And in addition, this collection of random sequences xm and the y tilde are conditionally pairwise independent given u. So if I fix u, basically there is like an underlying Markov chain here that I have the set of, for every m in the set A, x and m u and tilde y n. So if I fix u and tilde, x and m and y tilde are independent, conditionally independent. So then the statement says that there exists a vanishing function delta of epsilon that goes to 0 when epsilon goes to 0, such that for every positive epsilon, the limit of the probability that for some m, the triple u tilde x and m y tilde is jointly typical with respect to the typical set of the original distribution goes to 0. Why I say for some? Remember, the union sign, union, means this condition is true if it's true for at least one of the m. So for some m. If there was an intersection, this would be for all. Union for some, intersection for all. And this condition, this probability goes to 0 when the set A is not too large. So when the R that defines the exponential size of the set A is less than this mutual information of x and y given u minus this quantity delta. Okay? So in other words, imagine the following. I generate a sequence u tilde, and jointly I generate a sequence y tilde according to some distribution. Then I generate many instances for m equal to 1, 2, 3, 4, up to 2 to the nr, many instances, random sequences according to this product distribution. Given u tilde, I generate the components of the x's. So I have this library of sequences. We will see that this collection of sequences is what we call a codebook. We generate this collection of sequences. And then I test. I take, for every m, I take the triple u tilde, y tilde, x, and m, and I ask, is this jointly typical with respect to the typical set of p, u, x, y? Yes, no. If it's yes, then this union event, if it is yes for at least one m, then this event is satisfied. So if it is not, it's not satisfied. And I'm asking what is the probability that this event is true. And it turns out that this probability goes to 0 for large n, as long as the set of possible x's is not too large. So as long as the size of the set, 2 to the nr, is smaller than 2 to the n times the mutual information minus a vanishing quantity, and the mutual information between x and y given u. Okay? As we will see, this lemma is the central step, gives us the central step to prove the channel coding theorem. We will see later. Now we are just concerned with the proof. So how the proof goes. Basically, we first define this event E sub m as the event that the random triple u tilde, y tilde, and xm are jointly typical with respect to the distribution u, x, y. Then for given m, let's consider the probability of this event, right? So this is again obtained by summing over all triple x, y, u in the typical set the corresponding probability, and the corresponding probability is the probability of ui, which we know here from here is this q u tilde y tilde, times the product conditional distribution of x given u, is the way x is generated, right? So this is the probability. Now we separate this sum over u, x, and y into a sum. Here there is a typo. I should have taken this x away, because this is the sum over u and y, and then I collect all the terms for given u and y. I collect the inner sum with respect to x here. And now what we have that the joint typicality lemma says whether this inner sum here is the probability that x is jointly typical with y given u is exactly the same statement. So we already know that since x and y have been generated conditionally independent given u, this probability is upper bounded by 2 to the minus n times the conditional mutual information of x and y given u minus some delta. And then at the end, so this is a common term, it can go outside, and then here we have just the sum over a subset of the possible u and y of their probability. This sum is at most 1 because we are summing a probability mass function, and therefore this will be the overall upper bound. Okay, so this says that every probability p of this event for every m is upper bounded by the same quantity. So at this point we just use the union bound. We want to bound the probability of the union over m of this em. This is less or equal than the probability or than the sum of the probabilities. But now each of these probabilities is upper bounded by this quantity, and then how many terms we have here? Well, the size of the set, which is upper bounded by 2 to the n r. So at the end, this vanishes if the exponent is negative, and the exponent is negative if this mutual information minus delta is greater than r. Then the exponent is negative, and then you have 2 to the n times a negative quantity. When n goes to infinity, this goes to 0 exponentially, and this proves the packing lemma. Okay. The intuition beyond the lemma is the following. Well, okay, that's a repetition of what I already said before. So, okay, I will take it away. Wait a second. What did I do? It's almost a repetition of what I said before. It's almost a repetition. Okay, maybe I should just revise this slide because I see that there is a. So, okay, if I consider a simple case and I say, you know, we have the same thing I said before, where the probability that two marginally typical but independent random sequences are jointly typical is 2 to the minus n times the mutual information. But now we have not just one possibility, we have 2 to the nr possibilities. So basically, what is the, imagine that I generate 2 to the nr such sequences, right? And then I say, what is the average number of sequences that will be jointly typical? Well, it's the size of the set times the probability of being jointly typical. So it's the product of this 2 to the nr times this, right? And now there are two cases. Either this average becomes very large, so in other words, the exponent is positive, and if the average becomes very large, it means that this probability is positive, or this average vanishes. So on average, I will find no sequence that is jointly typical, and so if basically 2 to the nr times 2 to the minus n times the mutual information goes to 0, well then basically it is reasonable that the probability that some of these sequences are jointly typical with a given independently generated y will also vanish, and this is what the lemma proves. Okay, so yeah, okay, this is not very well explained because there is some repetitions, but I will fix it later on. So okay, now we prove the last result of this very difficult chapter. This is probably the most mathematical chapter of the whole course. But once you understand these things and you know how to apply them, basically all the most proofs of the result that will follow will be easy and understandable. So this other result is called the covering lemma, and works as follows. Basically, is almost like the reverse problem. We want now to see that randomly generated sequences with the correct marginals if I generate enough, so if I generate a set that is large enough, the probability of finding at least one that is jointly typical with another sequence is in fact becomes large. So the lemma says the following: if I have now a triple of random variables, u, x, and x hat, and I pick epsilon and epsilon prime in this order, and I have two random vectors u tilde and x tilde generated according to a certain joint distribution with the property that this joint distribution put all the mass on the epsilon prime typical set for u and x. So if I sum over all u and x epsilon prime typical, this probability mass I get in the limit for n going to infinity, I get 1, which means that if I take two long sequences generated according to this distribution Q, the probability that they are jointly epsilon typical becomes 1. Now, I generate a collection, again, a collection of random sequences x hat m as before, where now 2 to the n r is a lower bound to the index set, so at least 2 to the n r n. And how do I generate these random sequences? As before, these are random sequences x hat are generated according to the product distribution or the conditional distribution of x hat given u. And x hat given u is, again, is derived by this joint. Once you have the joint u, x, and x hat, you marginalize with respect to u and x hat, and then you consider the conditional x hat given u. And the condition is that these random sequences are conditionally independent of each other and on x tilde given u tilde. So the statement says that there exists delta vanishing when epsilon goes to 0, such that for every epsilon greater than 0, the limit of the probability that for the intersection over all m of these events that u tilde, x tilde, and x hat m are not jointly typical is 0 if the set A is large enough. So if R is larger than the mutual information of X and X hat given U. So what this means, it means that if we pick this set large enough, so this probability going to 0 means that at least one of these sequences X hat M is going to be jointly typical with U tilde and X tilde. Because the probability that the intersection that they all are not jointly typical to 0, so it means that at least one will be jointly typical. Some of the sequences will be jointly typical in the limit. So the proof goes as follows. First of all, since U tilde and X tilde are randomly generated, we create an event E0, which says E0 is the event that our generated U tilde and X tilde are not jointly epsilon prime typical, sorry. And by assumption, because this probability mass function Q puts asymptotically all the mass on the epsilon prime typical set, well, the probability that the two randomly generated sequences are not in that set goes to 0, because otherwise, if it was not 0, then this limit would not be true. The limit of the probability with respect to Q of the epsilon prime typical set would not be 1. So the probability of this event E0 goes to 0 as n go to infinity by directly from the assumption. Then we consider the intersection event, intersection over all the m of these events, right? And then we break this the probability of this event. We want to prove that this probability goes to 0. So we break it into the probability of E intersect E0 and the probability of E intersect E0 complement. This can always be done. Every time you want to compute a probability and you have another event, you can always write this probability as the sum of the probability of the event you want to consider intersect this other event plus the probability of the first event intersect the complement, right? And this is because, because in general for any event E0, E0 union E0 complement makes the whole sample space, all the possibilities, and these two are disjoint. E0 and E0 complement are disjoint. So every event E can be written as E intersect E0 union E intersect E0 complement, and these two are disjoint, and therefore the probability of the union is the sum of the probabilities, and therefore we end up with this type of expression where you can always break an event into the intersection with respect to another event and its complement. Then if we remove one of the two here, we get an upper bound, because when you remove terms in the intersection, you are enlarging the event. So we get an upper bound like this. And now we know that this term goes to 0, so we really don't need to take care about this. So we will only focus on this part. And this part is the probability of E intersect the E0 complement. E0 complement is, you see, is the complement of this. E0 was the event that the U tilde and X tilde are not jointly epsilon prime typical, and therefore E0 complement is that U tilde and X tilde are epsilon prime jointly typical. Okay, so now what we can do, we take two specific U and X that are jointly epsilon prime typical, and then a specific A, and now we know that U tilde, X tilde, and this random X, the probability that this triple is jointly typical goes exactly according to property number 3 in the joint typicality lemma, and therefore is lower bounded for sufficiently large n by 1 minus epsilon times this exponential. Okay, you can check, identify the terms, and see that this is exactly what we need. So now we replace these, we use this in the probability of this thing that we want to compute. So what is this probability? Well, this is summing over all U and X epsilon prime typical, their probability times the probability of the event E, which is this intersection, right, for fixed U and X. Now we have that by definition, the X tilde are conditionally independent with respect when conditioned on U, and therefore we have that the probability of an intersection is equal to the product of the probabilities by this conditional independence, and therefore we have the product with respect to M of these probabilities. But now we have that each one of those, you see, we have this bound here. We have that the probability of U, X, and X tilde being jointly typical is greater than 1 minus epsilon times this exponential. Now this is the complement you have here is not jointly typical, and now we can basically upper bound this by 1 minus the lower bound. So we have 1 minus the lower bound, that gives me an upper bound to each of these terms, and then we have cardinality of A terms in this product, so I have 1 minus the lower bound raised to the cardinality of A. This gives me an upper bound to this product, okay? And now this product does not depend on u and x anymore, on specific u and x, right? So I have just to take the fact that this sum of this this is exactly the term that we know it goes to 1 by assumption here. So this can be eventually upper bounded by uh, by 1, and at the end we have this 1. So this is a very small quantity. Let's call this quantity z. So effectively this is 1 minus z, where z is a small quantity, raised to some number here, and this number is let's say alpha, okay? This number, okay? And it turns out that when z is small, I can use that 1 minus z raised to alpha is less or equal than exponential of minus alpha z, okay? So using this bound, this is 1 minus z, so this part here is 1 minus z to the alpha. I use here alpha, so is exponential minus alpha times z, right? And it turns out that this alpha, so this cardinality of A that I call alpha is in fact lower bounded by 2 to the n r. So if I replace the lower bound here, I just make this term bigger, so this is still even more an upper bound. And finally, I find this upper bound. And now you see that if this quantity so this is a double exponential, the exponential of minus 1 minus epsilon times 2 to the n times something, right? Now, if this exponent in the inner exponential is positive, this exponential becomes very big. Here we have a minus sign, and this exponential then becomes very small. In fact, it goes to 0 doubly exponentially, so it's super fast, okay? So the last expression, it vanishes if the exponent inside the inner exponential is positive, so we have this condition, and this is exactly what we want to prove, because in this way we have proven that that probability that we want to show to go to 0 goes to 0 as long as, you know, R is greater than the mutual information of x and x hat given u plus a vanishing quantity delta of epsilon, okay? So the intuition behind the lemma is very similar as before. Forget about u for a second. Let's make it simpler. Let's have only x and x tilde, right? X and x tilde are, sorry, x and x hat are distributed according to a given joint distribution. And now we generate x hat according to its own marginal distribution. And then we ask, okay, what is the probability that x and x hat are jointly typical? Well, we already know that these will be 2 to the minus the mutual information. But now we generate a codebook of size 2 to the nr of these x hats. And what is the probability that at least one is jointly typical? Well, we want that again, if the set is large enough, so if the product of the size of the set times the probability of being jointly typical becomes large, then we know that this that there will be at least one such sequence that is jointly typical with X, and so we want that R is bigger than the mutual information. So exactly what is written here. Okay, so that's the intuition. So okay, this ends this chapter. Admittedly, this is another chapter that builds a lot of tools. At the moment, you don't really understand why we do this and how we will use this, but you will see in a moment, in fact next week, when we talk about the channel coding and the channel capacity, that we will use in particular the packing lemma to prove the existence of codes that achieve channel capacity. And then later on when we talk about the source coding and something called a rate distortion function, we will use this covering lemma to prove the existence of rate distortion codes that achieve the rate distortion function, which is the best possible compression rate with a certain distortion, so lossy compression. Okay, so we stop here, and this is it for this week.